All right, man. 10-2 in Advanced Algebra 2, doing a little probability and some sets. A lot of stuff we've done before, so not the hardest thing in the world. So little basic definitions first. All the possible outcomes in some sort of event is called the sample space, so you'll hear us talk about that all the time. And when we're when we're finding basic probability, the way we find that is what you want to have happen divided by the total outcomes in that situation. So let's dive in. It isn't our first rodeo with some of these things. Calculate the probability of the given event. The jar contains 32 red marbles and 28 blue marbles. What is the probability that a randomly selected marble is red? So we have to find our total, and our total right here, we just add those up. That is a big old 60 in that situation. So we got 60 marbles, and we want a red marble. So the probability of a red, some of us would like us to write you like that. Miss Dinahan, I know for sure, likes things written this way. We want to pull a red. There's 32 out of 60 total, and if you don't know how to reduce that, you can just do 32 divided by 60 in ye old calculator, do a little math, enter, and that'll change it to a nice reduced fraction of 8/15. So we're going to leave these probabilities as a fraction today. We get 8/15. A letter in the word restoration is randomly selected. What is the probability of selecting a vowel? So we got to go count out all our vowels, A, E, I, O, U. So here's 1, 2, 3, 4, 5 vowels. So the probability of a vowel is going to be 5 out of total letters. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And that does not reduce, so we're just going to leave it 5/11. A day in the month of January is randomly selected. What is the probability of selecting a prime number? Well, some basic skills. We need to know that January has 31 total days. Right, so there's 31 days, and we have got to find a prime number. Remember, a prime number is a number that is only divisible by itself and 1. So I'm going to just list them all out. So we can get 1st of January, that's a prime number. 2 is also a prime number, and 3 is a prime number. The next number is 4, but 4 is not prime because there's other numbers that go into 4 besides 1 and 4. So 5 is a prime number. 6 is not prime. 7 is. 8 has other numbers that go into it. 9 has other numbers. So work your way out to find the primes that go from 1 to 31. Please pause the video and get that done. And I appreciate those of you who actually found them. You other little cheaters that just waited to see what they were. Shame on you. So these are all the primes: 13, 17, 19, 23, 29, and 31. None of these numbers have anything that goes into it besides 1 and itself. So there is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 of those. So 12 out of 31 is our scenario on there. I don't really care personally if you put this probability of whatever, but I care about this, and it does not reduce in that case. So 2 dice are rolled. What is the probability that the sum of the 2 dice is at least 9? So what we can do is make our good old-fashioned chart in that situation. If you wanted to, or I just kind of did it like this. So to roll a 9, obviously you can roll a 10, that's bigger, an 11, or a 12. If you think back to when we did our dice probability, we knew that there's only one way to roll a 12, right? That's getting a 6 and a 6. And then to roll an 11, the chart just kind of went diagonally, so there's one more way than that, and then there's one more way than this to roll a 10, and there's one more way than this to roll a 9. And once you get to 7, it goes backwards in that scenario. So you can draw the chart out if you wanted to, or if you just kind of think, it's like, hey, I'll show you real quick. And thanks to the power of editing, you can see here's that one way to roll a 12, and as you look diagonally, there's 2 ways to roll an 11, 3 ways to roll a 10, and 4 ways to roll a 9. I've made this chart many, many times over the years, so I just kind of know. It's like, okay, then there's going to be 5 ways to do this and 6 ways to roll a 7. Then you got to start going backwards because there's less ways to roll a 6, less ways to roll a 5, a 4, a 3, and a 2. So I'm just going to add all these guys up. There's 4, 5, 6, 7, 8, 9, 10 ways to roll something that's at least a 9. They're right here. There's all 10 of those ways out of the 36 possible. Sorry for the pen drag. And if we reduce that, that is going to be 5 out of 18. Again, you could use your calculator to reduce if you wanted to. Okay, the old standard deck of cards is next, which isn't as standard as you think. There's not as many card players as there used to be back in the day. So just to kind of give you a little basics about cards, there's 4 suits called spades, hearts, diamonds, and clubs. Some people are so inexperienced that they call the spades shovels, which they're not, and they call the clubs like puppy dog's feet, but we're pretty good with what hearts and diamonds are. But we got spades, hearts, clubs, and diamonds. And in every one of those suits, there's 13 cards. There's ace, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then you got your face cards, jack, queen, and king. The reason why they're called face cards is because they literally have a person's face on them. So there's face cards. There's 13 spades, 13 hearts, 13 diamonds, and 13 clubs. That is a total of 52 cards. What is the probability of drawing a heart or a club? Well, or is a fancy schmancy thing in mathematics that means that we want to add these things together. So what we'll do is we will say the probability of drawing a heart is 13 out of 52, and the probability of drawing a club is 13 out of 52. And we add those together and we get 26 out of 52, which can definitely reduce to be 1/2. Half of these cards are hearts and clubs, right? Because there's an even amount of each one. So 1/2 is the probability of drawing a heart or a club. But for future problems, you might hear things about face cards. Remember, that's just the jack, queen, and king. An ace is not a face card because it doesn't have a person's face on it. So, all right, let's try again. There are 8 books lettered A through H on the shelf. If Scott randomly chose 2 books, what is the probability that he chooses books A and B? And is a magic word that means multiply. If I could spell it. Multiply. And if you go back here, or was an add situation. We added those probabilities together. And is a multiply. So, here's what we'll do. We'll find the probability of each one. Probability of A, that if he just randomly picked a book from the shelf, the probability that it was book A, well, since there's 8 total, and one of those books has an A on it, it's 1/8. And the probability of book B is also 1/8. And all we have to do is multiply those together. 1/8 times 1/8 is 1/64 in that scenario. So, and means multiply. You might see it in some future math classes as an intersection. You know, remember the old disunion greater than or? Or is a union of sets, means add, and is an intersection of sets, so that means to multiply things together. FST, you'll deal with some formulas for that stuff. Here in Advanced Algebra 2, we're just doing them the quick way. And then another concept today is called the complement of an event. The complement of an event is this. It's where outcomes in a sample space that are not included in the defined event. Since the sum of all the possible probabilities of a sample space is 1, like there's a 100% chance of like everything happening, then the probability of an event not happening, that's usually what the complement means. It means, okay, what it would mean if it doesn't happen is 1 minus that. And the indication is this weird little bar above it. So this is the probability of the complement of E, like bar E. Right? If there's an event named E, the probability of the complement is 1 minus that. So let's use a real life example to make that make sense. The probability it will snow tomorrow is 7 out of 20. What is the probability it will not snow? So to use language in mathematics symbols, it would probably do this. The probability of snow equals 7/20. Well, the way they'd write it to find the complement is the probability of it to not snow in that scenario. So a little bar above the S. That's going to be 1 minus 7/20. Well, we know that this is going to turn out to be 13/20 because it's 20/20 take away 7/20, which is 13/20. So if there's a 7 out of 20 chance that it's going to snow, then there's a 13 out of 20 chance that it's not going to snow. Here's another one. A month of the year is randomly selected. What is the probability of getting a month that does not begin with the letter A? Now, there's two ways to find it. You could definitely count up all your months that don't begin with A. Obviously, I wrote them out by snipping this, so if you didn't know your months, you'd have to write them all out. But you could just literally count them up, the ones that don't have an A, or you could count up the ones that do have an A. It's just April and August in that scenario. So April and August, we got the probability of an A being 2 out of 12, which is 1/6. So the probability of that not happening is going to be 1 minus that. So probability of A not happening is 5/6 in that scenario, because it's this is 1/6, so there's got to be a 5/6 chance. Again, you could have done that by saying, okay, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 months that don't start with A, so it's 10 out of 12, which is 5/6. So either way works. It's just sometimes it's easier because there's so many things to count up. Like we had to count up 10 of these, which really isn't that much. But sometimes it's easier to count the opposite of it and then do the complement. So if a spinner was equally spaced in sections numbers 1 through 16 is spun, so we got a spinner, there's 16 sections on it, and they're all the same. Find the probability that lands on a number that is not prime. Well, you could figure out which ones are not prime. We could also figure out which ones are prime. Since we kind of did that earlier, we went 1 through 31. We already have that list. 1, 2, 3, 5, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So these are our prime numbers. And we can do the probability of a prime would be 1, 2, 3, 4, 5, 6, 7 of these out of the 16 numbers. So that means the probability of it not being prime would be 9 out of 16. Again, you could have counted out all of the ones that were not prime, so you could have went 4, 6, 8, 9, 10, 12, 14, 15, 16, and that would get you to the same thing. But see, a dude like this, it's so much easier to use the complement because they say 2 dice are rolled. Would you believe there's 36 different possibilities when you roll 2 dice? We've drawn it out many times. What is the probability of not getting doubles? It's probably easier to figure out what the probability of getting doubles is and then doing 1 minus that. So you could have a 1 and a 1. You could have a 2 and a 2. You could have a 3 and a 3, a 4 and a 4, a 5 and a 5, and a 6 and a 6. Wouldn't you believe that's the only way to get doubles? So there are 6 of these out of the 36 possibilities, which is really 1/6. You got a 1/6 chance of rolling doubles. So the probability of not rolling doubles is going to be 1 minus 1/6, which is 5/6. There's a 5/6 chance of not rolling doubles in that scenario. So that one was much easier to figure out the probability of the opposite thing first and then doing 1 minus it. Using the complement is what that's called. And finally, we do a little bit of set notation, which we did some of this earlier this year, but this is more with probability. So we've got the union, and we've got the intersection of these guys. And then right here with the P in front of it, they've got the probability of landing in the union, the probability of landing in the intersection. Like I said earlier, the union is an or statement also. Still goes back to that old phrase, disunion greater than ors. And the intersection is an and statement. You'll do much more of this in FST if you even choose to take that class. So here's set A, meow, and here's set B, meow, meow. They say find just the union of those two. So we're going to put them all together. We're going to put them in these set brackets, and we're not going to list anything twice. So I also personally like to put them in numerical order. So it's 1, 2, 3, 4, 5, there's no 6, or there is a 6, excuse me, 6, 7, but see 7's in both sets, right? So we don't list it twice, 8, 9, and then a 10. So we listed the numbers 1 through 10. That's the union. Everybody that's in A, everybody that's in B, but don't list anybody twice. The intersection of those two are only the guys that are in there twice. So here's a 7, there's a 7. Here's an 8, there's an 8. And there's nobody else that's in there twice. So we'll put those in a set. How many elements are in the union? Well, we just count them all up, and there are 10 of those. Why is the number of elements in set A plus the number of elements in at B, why is it not that? Why is the union not this one plus this one? Well, we've talked about it. That's because there is an intersection of those, right? So there is some overlap. So due to the overlap in the sets. I have bad handwriting with this pen, so I have pretty good handwriting normally, but this pen is tough to write with. Then the formula for the number of elements, so that's what this means. This N right here, that means the number of elements in the union. So the formula for that is going to be, well, it's going to be the number of elements in set A, boom, plus the number of elements in set B, and then you take away the number of elements in the intersection, right? That's exactly what you could do in the intersection. So there was 1, 2, 3, 4, 5, 6 of these, 1, 2, 3, 4, 5, 6 of these. You add those up and you get 12, and then you take away the 2 guys in the intersection and you get your 10 back, right? So N in front of there means the number of people in that set. So let's do that, given this set of numbers. So here's our set all together. This is everybody. 0 through 9. All, I think. 1, 2, 3, 4, 5, 6, 7, 8. Yep. Let A be these guys and B be these guys. What is the probability that if all of these green hogs right here were in a hat and we pulled it out, what is the probability we'd get a guy from set A? Well, there's 1, 2, 3, 4, 5 of these dudes. That's what we want. We wanted to pull somebody from set A. And there was 10 total out of all of the numbers in the entire thing that we were choosing from. So 5 out of 10, which is obviously 1/2. What is the probability of pulling somebody out from B? So 1, 2, 3, 4, 5 of those guys. Out of the 10, there was a 1/2 probability of that happening. But here, finding the probability of pulling somebody out in the union, what we got to do is probably find the union first. We got to unite A and B together. So I'm going to start. There's a 1. There's a 2. There's a 3. Oh, he's in there twice, though, right? There is no 4, so be careful. We're not doing that whole trick of just listing them all. There is a 5. Meow. 6. Yep. 7. Got him. He's in both. 8, none of them. 9, got him. So there is 1, 2, 3, 4, 5, 6, 7 of these guys out of the 10 possible numbers that we're choosing from. So there's a 7 out of 10 chance. Probability of finding somebody in the intersection. Well, let's find the intersection. We saw 3 was in there twice. Boom, boom. 5 was in there twice. And 7 was in there twice. So it's 3, 5, 7. And then that is a 3 out of 10 chance. Then the probability of, remember this means something in not A. So we already know the probability of A. It's kind of weird that we did this out of order, but if you have the probability of A, you can find the probability of somebody not being A by doing 1 minus it. Well, 1 minus a half is still a half. So that's kind of weird. The probability of not being in B is 1 minus this guy, so it's still a half. So, interesting. One last one, baby. 2 dice are rolled. Yes, love rolling dice. Let A be the event that doubles are rolled, and let B be the event that the first dice shows the number 5. So we're going to have to physically write our sets. Now we're going to do this kind of fancy. It's going to look weird to the naked eye, but we understand what we're doing. To write our doubles, like like rolling a 1 and a 1, we're going to write it like this: 1 and a 1, even though that looks like the number 11. 2 and a 2, even though that looks like a 22. 3 and a 3, 4 and a 4, 5 and a 5, and a 6 and a 6. So they look like just plain Jane numbers, like 11, 22, etc. But we understand we're rolling dice here. Part B, set B says the event that the first dice shows the number 5. So that means we could roll a 5 and a 1, a 5 and a 2, a 5 and a 3, a 5 and a 4, a 5 and a 5, and a 5 and a 6. Because the first dice had to be a 5, we could roll with that. So I would let you, remember there are 36 total out of this situation also. Why don't you pause the video and do the rest of this thing, and let's see how we do. Well, the probability of A is there are 6 guys in here out of the 36 total, so the probability of rolling doubles, which we already figured out earlier, is 1 out of 6. Probability of B happening, where you roll a 5 first on anything, there's 6 of these guys out of the 36 possibilities, so that is a 1 out of 6. Probability of A union B, we probably better find A union B first. So here it is. There was somebody listed twice. That was the 5 and the 5. So you could write them all out, or you could just get your total situation by doing total number in this plus the total number in this minus the guys in the intersection. So we could have done that also, but there is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 of these guys out of the 36 different ways to roll your dice. So there was 6 plus 6, take away 1. There was one thing in the intersection, which we can see that over here. It's just the 5 and the 5. That's the one thing in the intersection, so 1 out of 36, and that doesn't reduce at all. Probability of not getting something in A, well, if the probability of A is 1/6, then the probability of that not happening is 1 minus that. Same thing here, 1 minus the probability of B would be 5/6. So was a pretty quickie little lesson. Let us know if you have any questions. There's some questions on the homework that talk about like flipping coins also. So let's just say that we were going to flip 3 coins, and they asked you to write out the sample set. Some of you have done this in math class already, some of you have not. So like if you're flipping 3 coins, there's only 2 outcomes, heads or tails. So what could happen is you could flip a heads, and a heads. Like all of those are heads. You could also flip a heads, and a tails. You could do a heads, a tails, and a heads in that situation. See, the first guy turned out heads every time. Then you could have done tails, tails, tails if you wanted to. Tails, tails, heads. You could do a tails, head, head also in that situation. So to figure out how many outcomes, see I only have 6, it's like, dude, how many am I supposed to have? Remember, it's the number of choices you have to the number of coins that you got here. So you're going to flip a coin 3 times, right? So you've got a first choice, a second choice, a second choice. It's 2 times 2 times 2. So there's supposed to be 8. So you can see I'm missing some right here because I don't have a tails, heads, tails, right? I was missing that guy, and I'm missing somebody else. So I'll let you figure out who else I'm missing, so that way when you want to answer some questions about flipping coins, you kind of have a clue. If there was 4 coins, you'd have to write 4 letters in that situation and figure out how many possibilities. There should be 16 different outcomes. That's the sample space. So that'll help you if we haven't talked about flipping coins yet in class. Other than that, let us know if you have any questions. Have a good one.